So we know that sequential consistency maintains human intuition, but we also know, or sort of can guess, that it's difficult to implement. So are there other memory models that can provide similar kind of intuition but be implementable? Well, the first one, which is almost intuitive, is called the total store ordering. And this is the memory model that processors like Spark and x86 processors almost implement. For all sort of reasonable discussions, we can say that Spark and processors and x86 processors implement total store ordering. In total store ordering, we maintain a global ordering of stores similar to sequential consistency, but loads can be bypassed these stores and then can be carried out in any kind of order. So global interleaving for all stores from different threads. Programmer's intuition almost maintains, so flag synchronization and store causality works, and Decker's algorithm does not work because the loads can bypass stores which it relies on. It's implemented by having the store buffer and putting store off the critical path, and coherence implementation is exactly the same as for sequential consistency. So a store buffer here is put on the path to the memory. You have to have, for every load that you make, you have to check entries in the store buffer if the load can be satisfied from the store buffer. Otherwise, the program order will not be maintained. So the Decker's algorithm will not work because the question is, does the write become globally visible before the read is performed? And this is not true, because the store here of A might lie in the write buffer, and then this B's read here will bypass that store, because there's no relation between them, so it will not be caught. And therefore, this reordering might happen by hardware anyway. So total store order will not save the world for the Decker's algorithm. If you want to write Decker's algorithm and similar, you need to insert a memory barrier. And all processors have this kind of instruction, because all processors in one way or another have a relaxed consistency model and does not obey sequential consistency. So a memory barrier, in its simplest way, will simply wait here until this store of A here has been globally performed. In TSO model, it means that you have to wait until the write buffer has drained. And then this one will work. So the memory barrier tells the hardware not to start the load until all previous stores have been globally ordered. So this means that this algorithm behaves like sequential consistency while these memory barriers are in place. Another model implemented by, for instance, the PowerPC processors is weak or release consistency. They are sort of slightly different, but for most purposes the same. So in this kind of memory model, the loads and stores are totally unordered. Only ordering you have are with synchronization accesses like locks and memory barriers and things like that. You have not maintained the program's intuition. The flag synchronization will not work. Causal correctness will not work. Decker's algorithm will not work unless you put more memory barriers in the code. It provides for better performance, but also provides for interesting bugs unless you use programming languages that implement higher model, like C++, 11, Java, OpenMP, which I'm coming to. these languages or extensions, they all implement some kind of memory model that can build even on a weak release consistency model in a good manner. So if the flag synchronization algorithm is to work for weak release consistency model, we need to put the memory barrier here and here. We also have to make sure that flag is not register allocated. And in fact, you will probably need a mem barrier also here. Causal correctness needs mem barriers here, here, and actually inside these